Good afternoon, everyone. I'm Biyuan from Tokyo Institute of Technology. Now I'm going to present our short paper, Sensor Glove Implemented with Artificial Muscle Set for Hand Rehabilitation. Stroke is a potentially fatal event that occurs when there is a shortage of blood supply to the brain. According to the data published by the University of Washington, the death rate of stroke in Japan reached 13.1% in 2017. And ranked as the third leading cause of death. It is also a major cause of disability. At least half of the surviving patients are left with physical impediments to the point where support or rehabilitation exercise is required for day-to-day living in the post-stroke stage. The traditional rehabilitation treatment in the post-stroke stage is usually aided by the occupational therapists. Nowadays, lots of automatic assistive devices have been introduced to integrate with the work in order to improve efficiency and effectiveness. Finger grip and release is one of the most common hand exercises for stroke patients. According to the previous research, bilateral exercise in hand rehabilitation is a potentially beneficial training paradigm. Our proposal is inspired by the researchers above. The aim is to help post-stroke patients learn to control movements and postures of fingers. When stroke happens in the right brain, left upper limb might be affected. Our soft exoskeleton glove is worn on the impaired hand, and sensor glove is worn on the healthy hand. And the data transmission from sensor glove to artificial muscle is via serial communication on a computer. First of all, let's have a look at the sensor glove. We implemented the bend sensors by flex point. The difference of length is in order to adapt to different joints. The glove is sewn using fabric which can be stretched in both horizontal and vertical directions so that it can fit different hand sizes better. There is an extra layer sewing on the back side of the glove that only follows the locus of fingers to provide the space for housing bend sensors. Upper right picture is a dissection of fabricated sensor glove to illustrate how the sensor is located. In the bottom left picture, the white dotted line sketches the contour of the extra sewing layer to house the sensors, and the bottom right picture demonstrates the full appearance of the glove. Next is the actuator part of the proposed system. This is a soft exoskeleton glove, which has 20 control degrees of freedom, 4 for each finger to support extension and flexion. 20 pieces of mechanism muscle are bundled up through 3D printed sheaths on the wrist and elbow. The integrated system is shown in the picture. There are master side and slave side in this training strategy. In this schematic, assuming the right hand is in healthy condition, so acting as master, and left hand is the impaired side to imitate the reference motion produced by the master side like a mirror reflection with assistance of soft exoskeleton glove. In our system, both hands will be involved in the training. The hand in healthy condition provides finger movement and recorded by the sensors. Data was transmitted to the computer via an Arduino Mega board, and the computer sends received data to the second Arduino board to control the air pressure of muscle tubes. The amount of air supplied to the muscle is represented by a value ranges from 0 to 1023. In the future work, we would like to improve the control of artificial muscle to real-time mode, and the system could be connecting to some interactive systems such as VR and motion sensing games to satisfy different training paradigms while improving the entertainment. Last but not least, IMU sensor can be also integrated into the sensor glove to provide spatial information. That's all of my presentation. Thank you very much.